Recording. Happy Garbage Day, everyone. Welcome back. I see everyone has something cool to drink with them. What is going on outside? I know, right? I tell you what has happened. Mother Nature is mad at Starbucks. That's my theory. Mother Nature is going to be like, does the calendar say October? No, then I'm going to sweat the pumpkin spice right out of you. Like, no, it's too soon for this. So, happy last days of summer, whether we want it to be that way or not. And yes, those of you who are in the building all day are probably freezing because the AC is cranked, and then you go outside and then you die. So, you really can't win. But anywho, this morning I went through and updated grades and read through your answers for Formative Assessment number 2. So that is like where I'd like to start, if that works for everybody. We do that. Let me get that to the other window and get the screen share going, of course. Very important component. Come on. There we go. Drag my little mouse over there. And sharing the correct screen, always useful. There we go. All right. So my assessment of everyone's answers is that people felt pretty good about the first 3, and the 4th one was a little bit, I'm not sure what you're asking me. So we'll talk more about that one as in greater detail relative to the others. But let me get the, too big, there we go. Question number 1 of Formative Assessment 2 was, for a compound symmetry model, what is the pattern of variance and covariance over time? What did you write down? You all answered it. I know you wrote something. The same. The same.
Variance and covariance over time, so regardless of how many occasions we have, we will
Yes.
have 2 parameters.
Yes, same variance, and then separately, same covariance. So just in case that's not clear, I'm not saying the variance and the covariance are the same, it's just that each of them is the same over time. And there's only 2 parameters. Does that change if I had more than 4 occasions? No, does not. What are the 2 parameters? Random intercept. One more word on that? One more word on random intercept. There's random intercept, and then there's a word at the end of it. Starts with a V. Variance. Yes. Yes. And I'm making a point of that because the estimated parameter is the variance of the intercepts, not each person's separate intercept. So the random intercept variance counts as one parameter, even though it describes differences across however many people. Then the other one, said, also starts with an R? Residual variance. And likewise, we don't have separate E's as parameters, it's just one variance. So the random intercept variance is level ... Yeah, 2. Random intercept is between person differences in level 2. And residual variance then is level 1 within person. Those 2 summed together recreate the total variance at any occasion. And which of those 2 forms the covariance between any pair of occasions? And I'm watching the chat in case the Zoomers want to talk to me too. The random intercept does, which is weird to think that a variance forms the covariance, but what it's saying is that the only reason that the occasions are correlated is because some people are higher than others. So it's an explanation, essentially, for why there's covariance. So that's the simplest model for the variance that we would entertain for longitudinal data. Okay, any questions on that one? So far, so good. Unstructured. What pattern does it predict? I'll take gestures on this one if you don't want to use words. Yeah, whatever it wants, right? There is no pattern. This is a data recreation model. So it simply estimates the variance for each separate occasion, the covariance for each separate pairs of occasions. And this afternoon, the same idea is going to be known as the saturated model. Those words essentially mean the same thing. All the parameters have been used. And for 4 occasions, then how many would that be? 10. How'd we get to 10? How many of those are variances? 4. Yeah, 1 for each occasion. Then how many are covariances? 6. Okay, do I need to count correlations separately as parameters or no? Ooh, a tricky one. Do I need to add those to my tally if I wanted to say what the model predicted the correlations to be? No, correct. Why?
Correlation to standardized covariance?
Yes. Yeah, if I know what the covariances are and I know what the variances are, I can compute the correlation. So you only need to know correlations and variances or covariances and variances, and you can get back and forth across correlation and covariance. And so which you get across these various models depends on your software. For instance, R specifies everything in terms of correlations. SAS and Stata switch back and forth depending on whether the variances are heterogeneous. Okay. One aside about this, the idea that this is the data, the only situation in which it will match the data exactly is if you have complete data. Otherwise, this model returns what the variances and covariances would be under an assumption of missing at random, which means conditionally random after factoring in the information that you do have about a person. So to the extent that, say, Seth, you have attrition in your study and people don't come back, the variability that the model estimates, like at the last occasion, is not going to match the data. It's going to try to recreate what it would be had everybody came to every occasion. But for complete data, when you're using REML, they will match. Okay, any questions on that one? All right, moving right along. Number 3. How does the content of the variances and covariance over time in the R matrix differ if you have G holding a random intercept variance? So if you don't, how would I describe the contents of the R matrix in an R-only model?
That would be the total variance and covariance?
Yeah, the total, the marginal, the everything in one pile, basically. It doesn't try to separate out level 2 versus level 1, except in this compound symmetry case is a special exception to that. So our choices for R-only models would be unstructured, compound symmetry heterogeneous, toplets heterogeneous, AR1 heterogeneous. Those are the ones that we talked about. There's lots and lots of others. Those are just the most common that I've seen for longitudinal data. Now, if I add a G matrix, meaning that I take the random intercept variance out, I have a separate place for it, then what is left over in R? Let's hear from someone else who hasn't talked yet, because I feel like some of you want to talk, but you're just feeling a little shy. Like, I feel like you want to talk and you're feeling a little shy.
Level 1.
Yeah, level 1. Level 1, meaning just the within-person information, just the deviations around those person means. That's what's left in R. And so the rationale for doing it that way, for having that separation, is that the pattern that R needs is probably simpler after you take out the primary driver of the covariance over time. So then you might be able to get by with fewer parameters and do it more easily. So everything that we're going to talk about in this class from this point forward is going to be G and R. A random intercept plus other things that are going to be put into the G matrix as well. Okay, any questions on that? No? Good so far? All right, then the last one. So what can you do when you have balanced versus unbalanced time, and what can you do if you have equal intervals versus not equal intervals? So I thought, so while I was running this morning and trying not to die of heat exhaustion, this is the spreadsheet that popped into my head, which we're going to fill out together, and I will post after class. How's that sound? This is like me writing on the board in the hybrid environment. My handwriting is not good, and the Zoomers can't see the board behind me, so we're just going to type. So let's start with unstructured as the most general case. So does unstructured have heterogeneous variances over time or homogeneous? Hetero, yeah. So I'm going to say het as an abbreviation for heterogeneous variances. There is not a kind that has homogeneous instead. Like, that's not a choice that you would see. In theory, it could be a choice, but it would be unusual. What kind of pattern does the covariance have? Does it have anything to do with a lag? Yeah, so not a lag. I'm going to put it that way. So therefore, I'm going to fill in the last column here first. Because it doesn't use the idea of a time lag, do we need to worry about whether we have equal intervals? We do not. No. Because each pair gets its own covariance, and so each pair can be however far apart they are. However, so this is the however finger, by the way, the left hand, although is the right hand. However, does it require balanced time? Yes, it does, and it's because of the heterogeneous variance part. Each occasion has to have a separate variance. Therefore, each occasion is a discrete, separate, categorical thing. We can't have 1.5 and 1.2 and 1.29 and give them all separate variances. At some point, it's going to break. So we say yes to that. I'm going to add. There we go. Okay, with me so far? Now let's do compound symmetry. CS for short. In its usual form, as we've called it first, is it homogeneous variances or heterogeneous variances? Yep. Homogeneous variances. Is it based on the idea of a time lag in terms of the covariance pattern? No, it's constant, not a lag. So therefore, does it require balanced time? If everything is constant, regardless of how far apart things are, no, it does not. Because you have a random intercept variance and you have a residual variance, and it doesn't matter how far apart the time occasions are because everything is assumed to be constant. Does it require equal intervals? Nope, because everything's assumed to be constant, regardless. There is a constant covariance across all the occasions from the same person, no matter which they are. That's what the model is saying. Okay, what about compound symmetry heterogeneous? What variance type? Heterogeneous. What kind of covariance type? Yeah, still constant, still not a lag. So it does require balanced time because of the heterogeneous variance part. It does not require equal intervals. Deliberately skipping AR for now, Topolitz. The original version of it has homogeneous variances. And does it use lags? Yes. I'll put it this way. Uses lags because all occasions that are 1 unit apart have the same covariance. A separate covariance is estimated for 2 units apart, a separate one for 3 units apart, and so forth. And so because of this idea of 1 unit apart sharing a common parameter, that is an equal interval assumption. Otherwise, you can fit it, but it doesn't make sense. So yes. How about balance time? In theory, no, but in practice, yeah, because it's a software issue. It's a software issue. No one has programmed a continuous version of Topolitz that I can find, and it's not even in R as near as I can tell. If I do Topolitz with the heterogeneous version, so that'd be Top H is what it's called. So I'm going to add the H's on here. Then we have heterogeneous variance. It still uses lags. And so then it's both, so stricter in that case. Now, last but not least, I realized based on your answers that this has been confusing, AR1. So there are 2 versions of AR1 that you can find in software. One is based on the idea of a lag and uses equal intervals, and the other is the continuous time version that does not require equal intervals. So it depends on the software. The default version of this is homogeneous variances, and it does use lags. So it doesn't I would say it does in that case. And then if we do the special version, so this is the one in SAS, it's a spatial structure. In R, it's a separate command for continuous time. Then you can have unequal intervals and unbalanced time. But you have to look for that option. So basically what it boils down to is any time structure that's based on covariance patterns with lags requires equal intervals, or you have to somehow adjust to make the prediction change with the length of the interval. And there may be ways to do that in the software, or you may have to program it yourself in extreme cases. And this is usually a homogeneous structure as well. So I'm going to say continuous time instead for that. And save. Okay. Does that help clarify where I was going? Sometimes I swear I word questions badly just to see what you say as a thinking exercise. Like, where would you go with this? Because then that helps me choose better words based on your answers.
So Lisa?
Hit me.
Okay, so these are all ACS then, alternative covariance structures?
That's what I would call them, yes.
Okay, got it. For
Yep.
some reason, I was thinking the compound symmetry was like a baseline and the other is alternative, but that makes sense now.
No, that is also true. These top two have special names. Compound symmetry is otherwise known as univariate repeated measures ANOVA. Unstructured is otherwise known as multivariate repeated measures ANOVA. But when people say those words, they're usually talking about ordinary least squares estimation, which then means you can't have missing data. If you switch to likelihood estimation, then you can have missing data, but you still have these constraints with respect to what your choices are. So then the rest of these choices on here are only possible by switching out of ordinary least squares into something else. So maximum likelihood, the residual version is what we're using, or Bayes, which takes maximum likelihood and adds prior distributions to the estimation. So Bayes adds on to maximum likelihood. It's not something different. For those of you in the other class that I'm not teaching. It's all about the crossover across the classes, right? All right. Any other questions? Or did I answer your question, Allison? You good?
Yep, thank you.
Okay, cool. Anything else that you want to ask about or go back over with respect to homework, perhaps? Because that's the next thing on your agendas, is that's due next week. Do you have a question about that?
Yeah, so the AIC, BIC, negative two-log likelihood.
Yep.
Comparing those. So when would it be the case that AIC and BIC would be would change differently and move, like comparing across models, if that makes sense? Because wouldn't they kind of change together?
You would think. So the question was, let me rephrase your question.
Yeah.
When would you come to a different conclusion about which is relatively best if you used AIC versus BIC? The answer is that they will sometimes disagree, because the BIC, where it's log n, is a sharper penalty. For every time you add a new parameter, it's multiplied by that log of the sample size. And by the way, it's natural log. I've already troubleshooted this for a few folks. If you're doing this in Excel, it's ln, not log. Log is log base 10. Otherwise, if you're doing it in software, you'd have to see what the function is called in the software if you're making it do the math for you. Because the AIC has a penalty of 2 times the number of parameters. BIC is log n. So it takes more to make the BIC happy, basically. If you add a parameter, it has to really help. And yes, I have absolutely seen the case where you would come to a different conclusion based on what you looked at.
So would you rely more on the negative two-log likelihood?
Mm-hmm.
Okay.
I would. If it's a nested model comparison and it fits better according to your likelihood ratio test, then that should be the evidence that you need. Now, that being said, I have seen people be like, well, but the BIC didn't like it, so I'm not going to keep it. And that's your choice. Okay, other homework questions or model comparisons? Yes, in the back? Yes, so the question was, which models can be considered nested to use with likelihood ratio tests? Okay, the first rule is, which estimator are you talking about? If you are talking about ML, then you can compare any model that is nested in another model, whether it differs on the mean side in terms of its fixed effects, whether it differs in the variance pattern, or both. if you are talking about REML, R-E-M-L, then you cannot compare models that have different fixed effects, different mean sides, because REML maximizes the residuals, and residuals are defined after the fixed effects are already taken into account, so they're essentially on two different scales. So that's the first question is, am I talking about ML or REML? And if you see a difference that has to do with the mean side in REML, it's automatically wrong. Another one is the number of parameters. The models have to have different numbers of parameters in order to be nested. So like one example, CS versus AR, those are both two parameter models. They're just two different parameters in terms of the way they're set up, but you can't use a likelihood ratio test because you wouldn't have any degrees of freedom. Most of the others, though, can be thought of as nested. So, like, for instance, toplets versus toplets heterogeneous, that's an obvious case to me at least, because you're adding, do the variances need to differ across occasions, or can I just have one? And so you can think of the extra parameters as being differences relative to the constrained one, and how many differences would it take to fill out the whole matrix. But by that same logic, I could do something like CS versus top, because CS says constant covariance, and toplet says, no, I need n minus 1 of them. And so deviations from that constant shared covariance you can think of as nested. And if you can do toplets versus the heterogeneous version, you could also do something like CS versus toplets heterogeneous. Now that one I would not say is a useful comparison, but it's allowed. Can you guess why I would think that these two would not be a useful comparison?
So we are changing variance and covariance.
We're changing two different things. So if the heterogeneous version of toplets fits better, it could be because the variances need to be different, or it could be because the covariances need to be different, or both. So generally speaking, I don't like model comparisons where the answer is ambiguous as to what made the model better. But it's allowed. Like mathematically, you'd be okay. Yeah, I think that covers most of what I would have asked about. Does that help? Okay. Yes.
What is the main difference between toplets and AR1?
AR1 has one correlation that's responsible for creating all the lagged relationships by squaring it, cubing it, fourthing it, fifthing it. Toplets has a separate one per each lag.
Okay.
So toplets is, the diagonal is the one, and then every other off diagonal adds another parameter, whereas AR1, it's one for every off diagonal, because the one gets squared, cubed, etc.
And when we're doing like negative 2 log, or the likelihood ratio testing, it has to be the model with more parameters minus 2 parameters.
Other way around.
Other way around.
Yep.
Minus 1.
Yep, I was going to say that one too. Fewer minus more. Fewer minus more. Just pound that into your head, because the order works whether you're talking about log likelihoods or minus 2 log likelihoods. Fewer minus more. If you're in log likelihood, bigger is better, you would end up with a negative number out of that comparison, but then you multiply it by minus 2 and it gets to be positive. If you're starting with minus 2 log likelihood, then smaller is better. The difference will just be a positive number.
So REML cannot be used on the mean side.
Model comparisons where the models differ in their mean side, you cannot do using REML estimation. The minus 2 log likelihood is a different definition of height for what the residuals are, because the residuals are made differently. Question from the chat, are we supposed to answer all questions in the homework because in your instructions you also mentioned 16 points? Yes. The answer is yes, answer everything. I believe it's 10 points for the computations and 6 for the results. I think that's what it says at the top. And so basically I compute how many points you've earned based on the number correct you get of each, weighted by what it's worth. So since most of the work here is computing things, there's more points for that. But do answer all the possible questions that you can. You will get feedback on the non-computational questions after the due date passes. Then you'll get to see what you missed, if you missed anything. Okay, Anything else before we switch gears a little bit? Now, I know it's not fun to talk about the rules of model comparisons, right? Like, no one said, I want to go to grad school and learn about how to do likelihood ratio tests differently when I use REML versus ML. Like, no one said that in their application letter, I'm pretty sure. But just think of this as like a board game, right? If you get out a brand new board game and you want to play it, someone has to sit down and read the rules, right? The instruction packet, and then figure out what all the pieces do and how to play. So you have to learn the rules at least a little bit to start playing the game, but once you actually play the game, you learn the rules a lot better. So we're just starting to learn the rules. We're going to start playing the game and getting practice with it. That's the plan. Question? Or stretching? Stretching, okay. Stretching is good. All right, anything else before I change gears a little bit? Okay, then I will post this later on today so that you don't have to write anything down. We're done with that. Homework is due next week, and then after that I think is another formative assessment. I'm layering in the review because the first part of this class is very vocabulary heavy. And we have more vocabulary to add to our list today. Yay! But we get to start talking about the cool stuff. I think this is one of my favorite things to talk about, just the idea of random effects and what they do. It's one of those things, too, that I felt really good about myself once I finally felt like I understood it. Like I had climbed to the top of the mountain. It's like, you know, or Rocky on top of the steps, right? Question?
One more quick question, kind of related. So when you say negative log likelihood, smaller is better, do you mean more negative?
Yes.
Okay.
Yeah, it doesn't matter if you're on the positive side or the negative side of the number line. Smaller is better.
Okay.
More negative is smaller. Less negative is bigger.
Okay.
Yep. Yep. Okay, then I have lecture 5 to jump into, and this is one that's very long, so I've got some signposting as we change through sections, so this will be like the next 2 weeks or so. Just as a heads up, I'm not planning to rush through all of this today. So big picture first, and then some new notation. So back to this image again, the idea of fluctuation versus change. Now we're on the change side. And we're going to be here for like 2 months. Because the idea of fixed versus random effects, and then the idea of what kind of trajectory do you have and what are your choices for fitting that with lots of examples of those, that's what will take the most of the time, is the nonlinear change component. But the next 2 weeks here, we're laying the groundwork for the idea of random slopes in addition to random intercepts. So in terms of our job for building a model for time, the idea of an unconditional model is that's a word that gets used, the idea that we're just focusing on time. What is the change over time? What aspects of change show individual differences? So in the model for the means, time is going to be relevant. In the model for the variance, time is also going to be relevant. And it's not just about matching the pattern of variance and covariance, it's about thinking about the reasons for that in terms of discrete types of individual differences. So these models are making a theoretical statement for the reasons behind different variances and covariances over time. And what makes them super cool is that you don't have to have balanced data. You don't have to have equal intervals. These work regardless. So, in terms of the model for the means, up to this point, we've only talked about 2 choices. Everything or nothing. So empty is the word that we use when you only have a fixed intercept. So there's one parameter in the model for the means, in that case, the fixed intercept, and that shows up by default in every software package on the earth. The alternative that you know of is saturated means, sometimes called unconditional means, but the idea is that you're spending as many parameters as you have occasions. So you can either fit this as having one fixed intercept and then n-1 slopes. So little n is the number of occasions. So if I had 5 occasions, I'd have 1 intercept and 4 differences. That would perfectly recreate the 5. You can also kick the intercept out of the model and just have 5 means. That's an alternative that I've seen people do. It screws up your f-test if you're not careful, but that can be an easier way to get at it. And there are situations in which I would do it that way. But the point of the story is that you're spending all your degrees of freedom. So saturated means is something that's not always going to be possible. It's a balanced data idea. So if you don't have balanced data, one thing that I would recommend is to temporarily pretend like you do, temporarily round people into convenient intervals, just to see what the pattern of the means looks like. Then you'll get a sense as to what the shape of the trajectory is that you're trying to fit, and that will help you go in the right direction. But don't round time otherwise, just to make a picture. That's it, just for descriptives. So where we are headed in this unit then is the middle. Can we come up with some kind of shape and the fixed effects that it takes to describe that shape that does as good a job as saturated means, but doesn't spend as many parameters? So the same kind of idea on both sides of the model here, but bringing in the mean side here. Because when people talk about change, they don't phrase questions about change as, I want to know if 1 is different than 2, and 2 is different than 3, and 3 is different than 4, and 4 is different than 5. They say, no, I want to know what the trajectory looks like. This idea of a function that summarizes the change. That's what we're looking for, is a function. And hopefully spending fewer parameters than all possible to fit it. So the choices that we will start with, linear, just to get the idea of fixed versus random in our heads. Then heading into polynomials, so time, time squared, that kind of stuff. Piecewise models, which are also known as linear splines. And then truly nonlinear models that contain asymptotes, for instance, exponential change or approximations thereof. The latter are trickier to fit, but they can be done. Okay, any questions so far? Okay, so big picture stuff right here. We're in the middle. We're working on building our choices in the middle. Same thing on the variance side. So compound symmetry is the simplest, unstructured is the most complex, and also it's only possible for balanced data. We're looking at choices in between. So last week we did the alternative covariance structure set of choices, the ARs and the Topolitzes and the whatnot. Now we're looking at random effects models which actually function the same way. Models that have random intercepts and random slopes for time fall within this middle ground here, where hopefully they're going to match the pattern that unstructured would have, but do so more simply with fewer parameters. And random slopes allow you to have unbalanced data and unequal intervals, which means maximum flexibility. All right, back to this picture then. Remember this from a couple weeks ago? Maybe. If not, it's back. So the empty model that has a random intercept only, that was one of the first things that we looked at. And in particular, we looked at how our conclusions about fixed slopes would change based on if we have the random intercept variance in the model versus not, right? Remember this now? Yeah, it's ringing a bell. So vocabulary time. When we have an empty means 2-level variance model where we have this idea of compound symmetry, level 2 random intercept variance, the symbol for that is tau squared, and then the subscript on it tells it what is the variance of. So any kind of random effect variance will be a tau squared something, and then I label it as, what is it? It's the random intercept variance specifically because it's U0 here. This is the idea that people differ in their means over time. So each person gets their own U0, that's why it has an I subscript. They get one U0, one shift in the mean that gets from the grand mean to their mean. The variance across people in these U's then is the model parameter that we estimate at level 2, and we're going to stick it in the G matrix from now on. So inter-individual differences, level 2 variance, this is also cross-sectional variance, because this is information that describes differences between people that you had going into your longitudinal study. Then at level 1, in the R matrix, we have the E's across time. And in the simplest case, we would say that E has the same variance no matter which occasion it is. And in the simplest case, no covariance. We can add covariance, as we talked about last Thursday, if we need to, and that idea will recur in this unit as well. But E represents within-person, intra-individual differences. It could be change, it could be fluctuation, we don't know yet. All we know is that they did not tell us the same thing every single time we asked. So E is the difference between where the person mean would take you and relative to where you are at each of these occasions. So level 1, E residual variance is within persons in the R matrix. Level 2, random intercept variance is between persons. Intercept represents mean differences, lives in the G matrix. And do you remember what it's called when we put R and G back together again? V. V for victory. Just remember it like that. Yeah. Okay. Now let me say all of that with a whole new set of equations. This is what I just said. This is what I just showed with a new set of notation attached to it. This is your very first multi-level model as it is written. So in comparison to an empty model that would be a general linear model, which looks like this. So this piece right up here in the top left corner, y sub I, if it's a general linear model, because each person has one y. E sub I, because each person has one e, if they only have one outcome. And beta 0 is the fixed intercept that represents the mean of that outcome y across people. Red, in all of my slides, indicates parameters that belong to the model for the means, fixed effects. Blue indicates parameters that are going to have a variance of some kind. So the colors matter in addition to the subscripts. So when we switch from y equals beta 0 plus e in a general linear model for one occasion to the bottom here, YTI, this is assuming more than one occasion per person. So at least two. So T stands for time, I stands for individual, whatever unit is being measured repeatedly, people in this case. Because each person has more than one Y, they have more than one E. So E is a time-specific and person-specific residual. Now this thing right here, beta 0 with an I, not a typo. In black, not a typo. Beta 0I is no longer a parameter. It is a placeholder. It holds other parameters. It's like a backpack. It's a place where you put things. So beta 0I is going to become how each person gets their own intercept. It has its very own equation at level 2. So the level 1 model describes what happens per occasion. The level 2 model describes what happens per person. The level 1 model is within, the level 2 model is between. Now we have a new symbol here. This Y-looking thing, that is gamma. It looks different depending on your font, but it is not Y, it is gamma. This thing is now going to be our fixed intercept. All fixed effects are going to be gammas. And I'm following the classic multi-level notation that Breik and Radenbush, Snyders and Bosker, and other sources have used. And again, I can draw gamma on the board, which is the other criterion I use. So now the fixed intercept is this gamma 0, 0. The subscripts describe what that parameter is doing at level 1 in the first subscript and what it's doing at level 2 in the second. So gamma 0, 0, the first subscript is 0 because it's talking about beta 0 at level 1. So in this level 2 equation for beta 0, every term starts with a 0 because they go with beta 0. The second subscript is indexing which term it is in the level 2 equation, where we start counting at 0. So gamma 0, 0 is the first predictor of beta 0. Because I'm going to have this random intercept to follow, the fixed intercept is not just the grand mean of the outcome. It is the mean of the person means, specifically. And that will be the same thing if everybody contributes the same number of occasions, but it will not if they don't. Then we have our friend U0. That's the same as that's been before. U0 is still our random intercept. It's U0 because it goes with beta 0. The second term is an I because it's a variable, not a constant. Each person gets a U0. So we refer to that as the random intercept. It is a person-specific deviation from the predicted intercept, the mean of the means. So beta 0I then is a placeholder for the fixed part plus the random part. The fixed part is the middle, the random part is the deviation. So beta 0I altogether is each person's intercept. But the way that it's made is with a common fixed intercept and then a person-specific deviation from it. So that's why beta 0I is in black, because it's not a parameter. It holds parameters. And if you're thinking, this seems like a lot for a really simple model, you're not wrong. A simpler way of writing it is down here with this composite equation, where the part in parentheses, I was using beta 0 to represent. I've got my fixed intercept plus my random intercept. That much gives me each person's mean. And then E is how far off your mean you are at that occasion. Okay, with me so far? All right. So then in terms of estimated parameters, there's only 3. Model for the means has 1, fixed intercept. Model for the variance has 2, level 1 E variance, level 2 random intercept U variance. Now this seems like overkill when it's an empty model. It quickly becomes useful though as we start to stack up more complexity into this thing. But this is the baseline. And this is the model absolutely that you would start with regardless, because this is the one that we use typically to calculate an intraclass correlation. As a reminder, what does intraclass correlation tell us?
Within group.
Within person in this class. Within person what?
Variance.
Not quite. Close. Stick a CO in front of that. Covariance, yeah. Interclass correlation, you can think of it as the average correlation of occasions from the same person. Or you can think of it as the proportion of total variability that's due to the random intercept between person differences. So if an interclass correlation is 0.7, that's 70% of the action is because some people are higher than others, 30% is because of the E's bouncing around the lines. And that would be called an unconditional correlation if you don't have anything in the model. That's just a straight description of the data. Yes, to the Zoomers, correct answers. Okay. Now here's what a saturated means random intercept model would look like using multi-level notation. This is not often written this way, but for completeness, since we've talked about this model, I wanted to throw it in. So saturated means is as many fixed effects as there are occasions. So if I had 4 occasions, if I make the last occasion my reference, then beta 0I would be the predicted mean at time 4. Beta 1I is going to hold the slope for how time 1 differs from that reference occasion. Beta 2I is going to hold the slope for how time 2 differs from the reference, and the same for beta 3. And because I have 4 betas here, I have 4 level 2 equations. In general, 1 level 2 equation per beta placeholder at level 1. However, 3 of these are essentially useless because all they hold is a fixed effect. So I could have just written that more directly like this. So this model says people differ from each other still in only one way in their random intercept for the mean, but that mean can be whatever pattern it wants to. This is still a parallel change model. So if I were to write it out removing the beta placeholders, it would look like this, which is what we saw in the ANOVA examples as well. All right, so then intraclass correlation. In the rest of what follows, we've got G and R. G is level 2 random effects variances, R is level 1 within person residual variances and covariances. Here is what the model looks like behind the scenes that would give us that intraclass correlation. So the letters that we introduced last week, I'll review. V. V is everything put back together again. What does the model say the overall marginal pattern of variance and covariance over time looks like? That's V. In about an hour from now, that's going to be sigma, by the way. Z is you're going to meet later on today. That is a matrix that holds the predictors to be given random effects. Right now, all we've got is an intercept. So this would be for somebody who has 4 occasions. The intercept is represented with a vector of 1s. If I turn it on its side, that's Z transpose. G is a matrix that holds our level 2 random effect variances and covariances. Only one thing in there right now, the random intercept variance. The purpose of Z and Z transpose is to make this the right size so that it can be added to R. So then R is within person variance. This structure right here is a very strict assumption that the residual variance is the same at each occasion. So that's why it's the same sigma squared E on the diagonal. And the zeros mean what? Yeah, no, the model says no residual correlation. It says the E's are unrelated. The only reason that they were related is over here now. Now, is that a testable hypothesis? Absolutely. Likelihood ratio tests. Doesn't have to stay this way, but this is the model that we're looking at. So when we put these things back together again, we get our friend V that has this compound symmetry pattern. So random intercept only means compound symmetry, means constant variance and covariance, means parallel growth. Parallel change, broadly construed. So then if I take the covariance version of this matrix and turn it into a correlation version, that's where we get our friend intraclass correlation. It's random intercept variance divided by that plus residual variance. If you were to compute the intraclass correlation from a model that uses saturated means, you would call it a conditional intraclass correlation instead, meaning after controlling for mean differences over time, this is the dependency. And some people say you should do it that way. So Pox is one author. He has a multi-level book that's been through several iterations over the years, and he's one of those people that says, no, because time is so important, you have to address that first and then do the intraclass correlation question.
So when we're doing likelihood ratio tests, why do we need a p-value? Why can't we just say, oh, there, this one is this value, this model is this value, this value is that value, and so therefore it's better or worse?
Because better has to be quantified relative to what would be expected based on just random chance.
Okay.
And the critical value comes from the chi-square distribution is that demarcation as to what would be considered unlikely to happen if the null hypothesis were true.
Okay.
Like if the models really were equal, how far away does this need to be like, yeah, that's pretty unlikely. It's the same reason that we use p-values for everything else.
Okay.
Or you can talk about overlapping confidence intervals or whatever you want to decide, but at some point you have to make a decision whether to keep a term or not.
Will it ever be the case where they're remarkably different in -2 log likelihood that the p-value is not significant?
No.
Okay.
No, because the difference in -2 log likelihood is treated as a chi-square test statistic.
Okay.
And then you get the p-value that goes with that distribution.
Okay, that makes sense.
Yeah. Now, people can quibble about which p-value it should be, whether it's based on a mixture distribution or a regular one, and that's like slide 60 or something in this deck.
Is that what
So,
we did last semester?
yeah,
Okay.
you did.
Okay.
It's back. And it'll come back in SEM too. Yep. So, I make this point about conditional versus unconditional because for some of you, when you analyze real data, you may very well have an intraclass correlation of 0. If you are in a context in which people are largely the same, for instance, there's a data set that I have an example with that's using infants and the number of words that you can say, and it starts at like 12 months. Any parents in the house here today? A few people, I know a few of the Zoomers are. How many words does a 12-month-old baby know how to say? One, maybe. How many?
Maybe one.
Yeah, dada, right? Maybe mama, but probably not yet. My son's first sentence to me when he was about 13 months old was "mmm," which translates as, Mom, please stop wiping my nose with that washcloth. I really don't prefer it. Thank you. "Mmm." But that's what you're at 12 months, right? So if you think about intercept variance, differences in the mean number of words the kids know, there aren't any. None of them can talk for shit at 12 months old, right? Then they start to spread themselves out as time goes on, and some people acquire words more quickly than others. So in that situation, you may very well have an intraclass correlation of 0, meaning there's no between-person differences. But after you address average change over time, what will happen is that the residual variance is going to shrink because you've explained part of it with change, and that's going to cause the intraclass correlation to go right back up again. So I generally prefer unconditional intraclass correlations, but I would label it as such. I think the most important thing you can do is be clear. You can say, this is the intraclass correlation after adjusting for mean differences, or you can say this is the intraclass correlation before adjusting for mean differences. Then the reader knows what you're talking about. Okay. Now, fun stuff. So we started with an empty model, but in order to characterize longitudinal data, that's not going to get us very far. We got to talk about the role of time. So I'm skipping a whole section of discussion that shows up in chapter 10 as an advanced topic about what time should be. This is something that you would have to decide based on the context of the study, what is relevant in terms of time, whether it's how long they've been in the study, how long they've been in school, how long they've had a disease, how long they've been in this situation. You know, it's completely context dependent. However, time, since the first time you measured them, you can never go wrong with that. So that's my personal preference. So the two questions that we want to know then, is there an effective time on average? So if I make a picture of what the model implied means are at each occasion, like from a saturated means model, for instance, or a rounded version, is that line something other than flat? If so, then I need fixed effects of time, fixed slopes of time. If the second question then, this is the new one that we haven't talked about yet, does that effective time vary across people? So does each person need their own version of whatever slope that turns out to be? If so, then we say they need a random effective time. So the vocabulary words to know: fixed means everybody gets the same, fixed means constant, random means everybody gets their own. And how people get their own is always going to be a combination of the common part plus a random deviation for how far off your version is. So just to start with, these ideas of vocabulary and what it would look like just using linear time. So first option here. So let's say that the x-axis in these pictures is time. The y-axis is whatever outcome you're measuring that's supposed to change. The heavy black line describes the mean trajectory for the sample, and the thinner black lines describe the predicted trajectories for different people. If this is what your picture looks like, then I would say you have neither a fixed effective time nor a random effective time. It's no fixed effective time, meaning not present, meaning would be estimated as close to 0 if you included it, because on average there is no change. The slope of the line is flat, so there is no fixed effective time present in these data, no fixed slope. By the way, the term effect is often used as a synonym for slope, but it's actually more general. Specific types of effects are intercepts and slopes. So I'm going to try to say slope, but we have a random intercept in all the pictures. It's the slopes we're focusing on for this purpose here. Okay, so no fixed effective time because there's no change on average. There's no random effective time because everybody is no changing the same way. That flat line holds for everybody. So we don't need a random effective time to fit these data. If we have a data set and we don't have a random effective time in the model, this is what it would predict: parallel change. Second one, top right. Now we're adding what a fixed effective time would predict. So a linear effective time would predict some kind of pattern of average change. Positive change in this case, could be negative as well. But we still don't have a random slope for time because that fixed trajectory holds for everybody. We don't need to give each person their own slope. This one works just fine. These are the only two scenarios on this slide in which compound symmetry could reasonably be expected to hold. Parallel. Now, bottom left, perhaps the most interesting case where we don't see a fixed effective time, but there is evidence for a random effective time. In this case, what's happening on average is misleading. On average, it looks like there's no change, but that's because some people are going up and some people are going down. So there is a random slope because that average line does not hold. People need their own version of the line. Random means everybody gets their own. So then your job would be to figure out, why is it that some people went up and some people went down? So this introduces a second way that people differ from each other, not just in their means, but in their slopes for change over time. And the last situation, a mix of both. Probably the most common. Yes, there is some degree of change on average, but people need their own deviation from that change. People need their own slopes. So we would have evidence for both a fixed effective time and a random effective time. Okay, how are we doing? Still alive? Still with me? Still awake? Zoomers? Rocking on? Okay. So one of the implications of this 2x2 setup here is that you can, let me say this. Just because you don't have a significant fixed effective time does not preclude you from going further to see if you have a random effect. You could end up at any 4 of these squares. The only catch is that because the way each person gets their own is always phrased as a deviation, if you want to have the random part of a slope in the model, the fixed part has to stay with it. Even if it's 0, let it be there and let it be 0. Because random is always phrased as a deviation from fixed. So the empty model that we started with would predict this square A here. That's what an empty model says. The empty model doesn't have time in it as a predictor, so it predicts a single flat line across all the occasions. The empty model that includes a random intercept does allow differences in the means. And so what's not in the picture are like all the little dots around the lines. These would be the best fit line through the dots. But this is where an empty means model would get us, just to this square right here. So from now on, we're adding stuff that will carry us over to B, C, and D. So here's B. Fixed linear time, random intercept model. So the random intercept part of the title and the model is the same. What we have added is a single fixed linear slope that describes the change in the outcome for each unit of time. So now my level 1 model still has YTI and ETI, 1 per occasion per person, but now I've got 2 beta placeholders. Beta 0I is how each person's going to get their own intercept. That's going to be defined by a level 2 model. Beta 1I is how each person gets their own linear slope for time, and that is also going to be defined by a separate level 2 model. 2 betas, 2 level 2 equations. So the beta 0I equation in the middle here, that is how each person gets their own intercept, and it's fixed plus random, just like before. So the fixed part is the common part, that is a constant to be estimated by the model, a fixed intercept. U0I is a random variable whose variance the model estimates. Over here for beta 1, it's just the gamma 1O. So gamma is for a fixed effect. The 1 is because we're describing beta 1 at level 1. The 0 in the second subscript is because it's the first term that goes into beta 1. And there's nothing else here because it's not random yet. So this is a parallel change model. We are allowing some degree of linear change by the introduction of gamma 1O, but it's still parallel change because everybody's supposed to change the same according to this model. So this is getting us over from A to B. in terms of what the model says we would see about the data. If I were to write out a composite model, then using parentheses to show the effects of the betas, the first beta 0 placeholder holds the fixed and random intercept part. The second one holds only the fixed slope. So beta 1I is just gamma 1O at this point in the model. One other catch. Previously, we talked about the idea of the fixed intercept and the random intercept as being person mean differences, right? But that only holds if we have no predictors in the model. But we've picked up a predictor for time. So now, what does the fixed intercept become? Time zero. Yes, the predicted mean at time zero from that line. Not the actual mean at time zero, but the one that where the line ends, wherever zero is. So right off the bat, you got to know where time zero is. How do you know where time zero is? Yeah, you pick. Put it somewhere. It is usually the case that time zero is the first occasion of measurement. Doesn't have to be. But I am presupposing that you have centered time so that zero is within the scale of it somewhere, just like any other predictor on the planet. So this is going to be predicted mean at time zero. This is going to be still the difference in the person means because of the parallel implication. So U0 in category B here on this previous page, U0 is specifically at time zero, but the implication of the model is that it'd be the same if it were anywhere else because of the parallel. So U0 is a constant shift. Okay. Questions? So speaking of things you learned back in linear regression class, what about R square for effect size? Can we do that here? Sure we can. Can we do it the same way? No. How many piles of variance are on my slide here? 2. So how many different kinds of explained variance am I going to have? 2. Yeah. So when we think about what the job is of a predictor, predictors are supposed to explain variance, right? Which variance, though, is which kind of predictor is it? In this case, let's say that everybody has the same time occasions. Let's say that the data are complete even. So it's like time 0, 1, 2, 3, 4. Is time a person thing or a time thing? Not a trick, because it's 1:35 and I know where our cognition's at by now. Not a trick. Is time a time thing or a person thing? It's a time thing. Okay, so in terms of my 2 piles of variance, which one is the time variance? Residual at level 1. So therefore, in terms of explained variance, which one should be reduced by the inclusion of time as a predictor? Level 1 residual within persons, yes. More generally, what we will see is that in this equation system of writing it, the predictor explains whatever residual is on its line. So anything you put that is a time-varying predictor, like time itself, is going to explain E-variance. So we can compute a reduction in how much E-variance we had in the empty model versus what we have now. And the idea of a per pile reduction is what's known as pseudo R square. And that, by the way, is not me being funny. That is what it's called. Like everybody calls it that. Because it can behave strangely. So it's like R square-ish is the way I would think about it. Conceptually, yes, but it can go up. So one of the first things that we will see in our example is some unexpected consequences of explaining the residual variance. So more generally, we can compute a pseudo R square for any of our variance components. By the way, they're called variance components when you're writing this up. They're piles of variance when I'm talking. Don't say piles of variance in your dissertation. Nobody will like that. So we are computing a reduction in each pile with this formula, what it was minus what it is versus what it was. So fewer minus more still. How much variance did we have before minus how much do we have now versus how much do we have before? There are various other versions that rearrange this formula, but this is the one that I like the best. So it's a reduction in variance. And by the way, in regular old regression with only one E, in linear old regression, this would be what you get if you use the mean squares rather than the sums of squares in computing residual variance. It's adjusted R-square. So there is a direct analog to how we would talk about it in regression. It's adjusted R-square, not the R-square that comes from the total sums of squares. The reason that we don't do it that way is to keep it positive. So we know that if time is a time level predictor, if it varies within persons, we're going to explain some amount of residual variance at level 1 by including its fixed slope. So the rules are the same in that regard too. Every time we add a fixed slope of a predictor, we explain some kind of variance. It's our job to figure out which kinds. However, if time also varies between persons, then it can also simultaneously explain random intercept variance at level 2. So when would that happen? Accelerated longitudinal designs. So if I go into an elementary school and I take the first graders, second graders, and third graders and I measure them all, and then I come back next year and I do the same thing, I have time in terms of grade that has passed since the study started. That's within persons. But then I also have time in terms of what grade you started at time 0. That's between. So the differences at time 0 between first, second, and third graders, that's a person thing. And that person thing would explain level 2 random intercept variance. How much older you are now than you started, that's a time thing. That's within, and that would explain level 1 residual. The examples that I'm going to show you this semester are going to focus just on residual with no between-person differences. That's a layer of complexity that we can do next semester in the advanced class. So when we include a fixed slope for time, level 1 residual variance should go down if there is some degree of change. And that would be our effect size that goes with that significance test, just like normal. And we could also take the t-test statistic for that slope and turn it into a partial eta squared or a semi-partial eta squared or whatever you want to do with that, or a d, for instance. So the same things that you would normally do, you can still do. It's just you got to keep in mind, like, what target do you have for which variance is being reduced. Now here's the crazy part. Anytime that you reduce level 1 residual variance, random intercept variance is going to go up. Here's why. The observed person mean difference variance. So like if you were just to not estimate anything, just take a data set, compute the person mean for each person, and save that to a new data set and calculate the variance across those person means, the answer that you get is going to be bigger than what SAS, R, or Stata gives you for between person variance. The reason is that it's trying to correct for how much of that person mean differences variance is actually just due to differences in within person composition. So the way that I can explain this, let's say that I take all of us, all the Zoomers, all the Roomers, and I divide us each into groups of 3 people, randomly, right? No pattern whatsoever. Got my groups of 3 people, and each group of 3 people, is that English? Each group of 3 people is going to compute the height of their group on average. And we're going to write all the heights on the board. I only got 4 minutes of class, so we're not going to actually write it out, but you can continue the thought experiment with me. Are all of the groups going to have the same mean height? No. They're randomly assigned, so it shouldn't be that different, but there's going to be some bobbling, right? Some fluctuation because of who happened to be in your group. So that bobbling, that fluctuation, it's adjusted for in the estimation by this term right here. residual variance divided by the number of level 1 occasions. So it's trying to approximate how much of the between persons variance is actually due to just residual. So this correction term starts to go away the more level 1 units you have, but for only 3 or 4 occasions, it's going to be fairly sizable. So the true estimate subtracts that off, and then we end up with a smaller number here. So what's going to happen is that anytime this residual variance part becomes smaller, less gets subtracted off, and the true estimate's going to increase. So the numbers from chapter 5 of your book, let's say that the observed person mean variance is 4.65. So if I took the data set, computed a person mean across time for each person, then asked for the variance of that person mean column, I got 4.65. Let's say that when I go to estimate a model, the empty model residual variance is 7.06, and I have 4 occasions. Well, let's say that then those numbers, when I subtract off that correction, is going to reduce my level 2 random intercept from the model to be 2.88. So it's less variance than there actually are among the person means in the observed data. If I add a fixed linear time slope, that, in this example, reduced the residual variance from 7.06 all the way down to 2.17. So that is a reduction of 69% of the residual variance. So now that correction factor has shrunk. So if I put it into the same equation to figure out what the random intercept variances be, it's much bigger now. So I tell you this because when you see your random intercept variance all of a sudden go way up, do not panic. You didn't do anything wrong. It's just math. It's going to happen. It is a consequence. And the extent to which you will see this depends on just how strong the effective time is in your data. So for this reason, because you can end up with a very different conclusion about how much intercept variance you have, some folks, like you, Pox, suggest doing your interclass correlation after accounting for fixed effects of time. It's a reasonable thing. As long as you explain to your readers which it is, then you're in good shape. So we will see this happen, and if the intercept variance goes up after including fixed time, the interclass correlation goes up too. Has to. All right. That's a good place to stop. So, questions on any of that before we call it a day? Zoomers, any questions? No? Cool. All right, then we're not calling it a week. We're just calling it a day because it's garbage day, which means I say happy Thursday or happy Tuesday. I'll see you Thursday. Messing up my own sayings. It's terrible. All right, thanks, folks. Let me know if you need anything.